Welcome to Part 7 of the CipherVibe Cloud Security Capabilities series. This episode explains runtime, detection and response, why it matters, how the capability works, which mistakes weaken it, and how to build it in a measurable way. Runtime security observes what workloads, identities, processes, and network connections actually do after deployment. It complements posture and vulnerability management by identifying active exploitation, malicious behavior, and control bypass in real time. The key idea is that a security capability is more than a product feature or a collection of alerts. It combines people, process, technology, decision rights, evidence, and continuous improvement. We will examine its architecture, operating workflow, failure modes, defensive controls, implementation roadmap, and useful metrics. Coverage is not the same as effectiveness. A dashboard can show thousands of checks while the capability still fails because evidence is stale, ownership is missing, or remediation is never verified. The business outcome should be explicit. Teams need to know which loss scenarios the capability reduces, which systems are in scope, and which remaining risks require a conscious decision. To understand runtime, detection, and response, start with its architecture and vocabulary. The capability should create a traceable chain from source evidence to a security decision and then to an accountable action. First, runtime telemetry includes process execution, system calls, file activity, network flows, identity events, orchestration events, and cloud audit logs. Second, behavioral detection models sequences and relationships rather than depending only on signatures or static indicators. Third, detection engineering defines hypotheses, required telemetry, logic, expected false positives, triage context, and validation tests. Fourth, response spans enrichment, isolation, credential revocation, workload containment, evidence preservation, recovery, and lessons learned. These concepts need shared identity, timestamps, provenance, ownership, and access control. Every summarized risk should link back to its source evidence and disclose missing information. A sound architecture separates collection, normalization, analysis, policy, workflow, and presentation. Teams can then test freshness, identity resolution, policy results, owner routing, and closure independently. Design for degraded conditions. Providers impose rate limits, schemas change, credentials expire, and events arrive late. A professional capability reports uncertainty and health instead of presenting incomplete information as fact. Trust boundaries deserve equal attention. Identify where data crosses accounts, tenants, regions, vendors, privilege levels, and administrative domains, then apply authentication, authorization, validation, encryption, and audit controls at those boundaries. A useful operating model for runtime, detection, and response follows a repeatable evidence lifecycle. First, map critical attack techniques to available telemetry and identify visibility gaps by workload type and environment. Second, create high-confidence detections with process, identity, network, vulnerability, and business context attached. Third, triage by validating asset ownership, exposure, expected behavior, related alerts, and recent changes. Fourth, contain with the narrowest effective action while preserving evidence and protecting control plane availability. Fifth, convert incident findings into new detections, harden defaults, tests, and preventive controls. The workflow does not end when a ticket closes or an API returns success. Security closure requires fresh evidence showing that the risky condition is gone and does not immediately recur. Ownership should be established before urgent findings arrive using service catalogs, business applications, on-call schedules, and escalation paths. Prioritization should explain the influence of exploitation, reachability, privilege, data, business criticality, compensating controls, and confidence. Repeated findings should drive changes to secure templates, defaults, libraries, identity patterns, and architecture standards. Define escalation points for missing owners, disputed priority, failed changes, and evidence that suggests active compromise. Those conditions should move into incident or risk governance rather than remaining indefinitely in a routine queue. The fastest way to evaluate runtime, detection, and response is to study how the capability can fail. First, high-volume telemetry without retention and query planning becomes expensive but unusable during incidents. Second, kernel sensors or agents may be unavailable on managed services, serverless systems, or restricted hosts. Third, response automation can destroy forensic evidence or interrupt production if confidence and scope are weak. Fourth, static thresholds miss low-and-slow attacks while broad anomaly detection produces excessive noise. Fifth, cloud incidents cross identity, control plane, workload, and SaaS boundaries that separate teams may investigate independently. These failures share a pattern. A local measure looks successful while the full outcome is weak. A connector, scanner, or repair can report success while coverage, exploitability, or recurrence remains unresolved. Measure whether the program improves important coverage, shortens exposure time, removes attack paths, and prevents recurrence, not how many alerts it produces. Exceptions need a reason, owner, compensating controls, approval, and expiry. Automation should reflect confidence, reversibility, blast radius, and business impact. Test both through controlled failure exercises. Correlate weaknesses instead of reviewing them separately. A moderate configuration issue, broad identity grant, exposed service, and sensitive data store may combine into a severe path even when no individual alert looks critical. A dependable runtime, detection, and response program uses defense in depth. No single scanner, policy, gateway, or agent should be expected to carry the entire outcome. First, define telemetry standards, health monitoring, time synchronization, retention tiers, and protected log destinations. Second, use detection as code with versioning, peer review, test data, attack simulation, and measured tuning. Third, correlate runtime behavior with vulnerabilities, identity, posture, exposure, and deployment context. Fourth, pre-authorize containment patterns, maintain forensic procedures, and protect break-glass access. Fifth, exercise cloud incident scenarios involving credential theft, workload compromise, persistence, and data access. Control design should include preventive, detective, responsive, and recovery layers. Together, they establish safe defaults, identify drift, govern containment, and restore service. Least privilege applies to connectors, agents, orchestration identities, data stores, and administrators. Scope, separate, monitor, rotate, and test their access. Every control needs an owner and test strategy. Validate it with representative assets, negative cases, simulated attacks, provider failures, and rollback exercises. Integrate controls with engineering through clear pull requests, owner routing, reusable fixes, documented standards, and fast feedback. Preserve an evidence trail from detection through decision, approval, change, and verification. That lineage supports investigations, audits, lessons learned, and fair performance measurement without forcing teams to reconstruct history from separate systems. A practical implementation roadmap for runtime, detection, and response should build trust before scale. First, prioritize crown jewel workloads and cloud control plane events before pursuing universal telemetry. Second, implement sensor health and a small set of validated high-value detections. Third, build triage views and containment playbooks with clear authority. Fourth, run adversary simulations and measure visibility, decision time, and containment safety. Fifth, expand coverage based on attack paths and incident evidence rather than raw event volume. The roadmap is incremental because a focused production scope lets teams validate evidence, ownership, workflow, and control safety before scaling. Useful measures include runtime coverage, sensor health, validated detection rate, mean time to contain, and repeat incident technique rate. Give every metric a precise definition, data source, owner, and known limitation. Pair lagging indicators such as exposure age with leading indicators such as coverage, control health, exception expiry, and secure template adoption. Maturity means the organization can discover important risk, explain it, assign it, act safely, verify the result, and learn from recurrence. Review the roadmap quarterly. Changes in architecture, threat activity, regulation, business strategy, and provider services can alter both priorities and assumptions. Retire metrics and controls that no longer guide useful decisions. For more cybersecurity market intelligence, research, and educational briefings, visit CipherVibe.com. CipherVibe is operated by Cloudsectech LLC. This video is general education, not legal, compliance, financial, or incident response advice. Never access or test systems without explicit written authorization.